Set packing is a famous combinatorial problem. The question is, considering a set U, what is the largest number of subsets in U which are all disjoint? Set packing is going to be an NP-hard problem, which means there is no polynomial time solution to solve it efficiently. So that's why we are going to use a non-deterministic approach to solve this problem. To understand simulated annealing, consider a particle on an energy landscape. The particle has a certain parameter called the temperature, which causes it to move around. Now we employ a Metropolis algorithm to determine the particle's movement. If the energy of the particle decreases by a certain move, it automatically accepts the change. If the energy increases by a move, the change is accepted with a probability proportional to e to the minus delta E by t. Let's state the problem more formally. Consider a set U and Vi be subsets of U. We will construct our Hamiltonian using two parts. Up first is the penalty term. We don't want Vi and Vj to have a common point. So every time Vi intersection Vj is not equal to phi, we apply a penalty of A. Since we want as many sets as possible in our solution, we apply a negative penalty of B. Here xi is a Boolean variable which holds value of 0 and 1 if Vi is included in the set or not. Here we must make sure that B is less than A so that it's never worth breaking the constraint to gain a reward.